Okay, hello ladies. So today we're going to talk about 7.6, which is solving equations using logarithms. And then we're also going to throw a little bit of interest in there because interest is kind of where we actually use this stuff in the real world. So our learning objectives for today, solve exponential equations using logarithms. Okay, so the next thing that we need to talk about is what we call the common logarithm. It's a logarithm that has a base of 10. It's kind of like the default for logarithms. So if you think like with square roots, we oftentimes will just use this radical symbol that we're used to. So this radical symbol here, which really we know identifies as index of 2. It's a square root as opposed to the cube root or the fourth root or something like that. It's just kind of a way that we kind of limit the things that we have to write because that's the most common. So the most common logarithm is log base 10. So oftentimes you'll see something written as log x. Log x. It's important to know that when it says log x, that really means log base 10, okay? So we're going to go to the next slide and take a look at some of those things. So on your calculator will default as log base 10. So in your calculator here, if you have log of 6, if you actually just type in log of 6, that will give you the log base 10. It would be the same as plugging into your calculator like we had practiced last week of log of 6 comma 10, where we put the comma and the base there. Okay, those two things would be the same thing on your calculator, so why plug in the extra 10 if you don't have to? Okay, so I'm going to give you guys a second to try plugging those in to number 1 and number 2. Plug those into your calculators, just make sure that you get out the right answer. Press pause if you need to. Okay, so for number 1, you should get 0.7782 if we're rounding to the nearest 10 thousandths. For number 2, the log base 10, even though it doesn't say a 10 there, it's base 10. Log base 10 of 0.35, you should get out negative 0.4559. So just double check on your calculators that you got that correct. And then you should be good to go with those, okay? Now, what if I wanted to evaluate something by hand? And I'm going to do this in a different color because I'm going to kind of have to impede a little bit on this space up here. So if you want to evaluate something by hand, the easiest way to do that is to set it equal to some variable. I'm going to choose x. You could choose whatever variable you want. Okay, now let's rewrite this logarithm in exponential form. What I oftentimes do is anytime that you are faced with something that's either a logarithm or an exponential piece that is challenging and you don't really know what to do, I would change it to the other form. So right now we're in logarithmic form. Let's change it to exponential form. I'm going to do that up here. So I'd have in exponential form, remember this is base 10, so I'd have 10 to the x power is equal to 0.0001. Okay, now our goal will be to try and make the same base here on the left-hand side and the right-hand side, base 10. And then what we can do is we can figure out what those exponents are. So in order to make this base 10, I like to turn this into a fraction. So this would be like 10 to the x power is equal to 1 over, well, this would be tenths, hundredths, thousandths, 10 thousandths. So this would be over 10,000. Okay, and 10,000, writing that with base 10, oops, that should be an x, would be 1 over 10 to the 4th power. And thinking back to laws of exponents, how do we deal with an exponent in the denominator? Well, we can move that to the numerator by making it negative. So x in this case would have to equal -4, which means that the log base 10 of 0.0001 is equal to -4. Now notice a logarithm can equal a negative number, but you cannot take the logarithm of a negative number. That's kind of what you were working on yesterday in your notes. Okay, so what we're going to do is we're going to practice solving for an exponent. The traditional method for doing this is by taking the log of both sides and then using the power properties of logarithms to help you solve. This is something that we're going to focus on when we get into pre-calc. I spoke with Ms. Spung and we both kind of decided that we really want you to focus on the definition of logarithms right now. And so I'm going to show you actually a way that you can solve these more basic questions using just the definition, okay? So as a reminder, it might be helpful to write down the definition of logarithms up at the top of your paper whenever you're working on this. I would write log base b of x is equal to y if and only if, that IFF stands for if and only if, base b to the y power is equal to x. So we're going to kind of use that as a reference for ourselves, okay? So coming down here to example 1, if I have 5 to the x power is equal to 62, what I'm going to do is I'm going to say, okay, this is an exponential form. I want to change this to logarithmic form. Watch what happens. If you change this to logarithmic form, you have log base 5 of 62 equals x. Logarithms always equal exponents. Logarithms equal exponents. Now, notice I have a logarithm. What I wanted to solve for in this original equation was the exponent, and now I'm solving for that exponent. Okay? So this is not something that we can do in our heads. We'd actually have to use our calculators for this. And so in your calculator, you could plug this in. We would plug it in as log of 62 comma 5. All right. And that is equal to 2.56, sorry, that 2 didn't write, 2.5643. Simple as that. So we're just using the definition to help us. All right, for this one, what is the solution of the equation 3 to the x power is, or plus 2 is equal to 17? Well, we need to first isolate the exponential part. So I'm going to subtract 2 from both sides. So we end up with 3 to the x power is equal to 15. Now, if you could change 15 to have base of 3, but we actually can't here. So this is when I say, okay, I have an exponential situation. I don't know how to do it by hand using that. So I'm going to change this to logarithmic form. So this would be log base 3 of 15 is equal to the exponent x. Logarithms equal exponents. So if we plug that into our calculators, we end up with x equaling about, this is a rounded value, 2.4650. 2.4650. If you plug this into your calculator, you actually get out 2.46497. So I went ahead and rounded up to 50 because the 7 would round up the 9, and then the 9 would round up to the 4. So we'd end up with the 50 there. Don't stress out too much about your rounding on this. I just wanted to fill you in on that. Okay, so now let's look at a more complicated question, okay? It's a word problem. It's actually not that bad, but we're going to use this idea of solving to help us out. So this is a half-life question, okay? So Seborgium-266 is a radioactive substance such that every 30 seconds, its mass decreases by half. So I know right there that this is a half-life problem. For a sample of Seborgium-266 with an initial mass of 82 milligrams, answer the following questions. So write an equation to represent the decay. So first of all, let's remind ourselves that for half-life, the formula is y is equal to a times 1/2 x over h being the half-life. A being the starting value. So I would say y is equal to my starting mass, which is 82, times 1/2 to the x power divided by 30 seconds in this case, okay? So the question is, how many seconds would it take to have 14 milligrams of seborrheium 266? So 14 milligrams would be what I have left over. So that's going to be a y value, okay? Remember, x is kind of representing the time here. So I am going to go ahead and plug that in. I'd have 14 is equal to 82 times 1/2 to the x divided by 30. So our goal is to solve for x, which is part of the exponent. So let's go ahead and isolate that exponential part first. I'm going to divide everything by 82. And I'm going to do my best not to plug anything into my calculator until I am at the very end. And the reason for that is that we don't want to have rounded values and then start taking operations on those rounded values. Then we lose some of our accuracy. So leave it as a fraction, leave it as an exact value. Don't plug it into your calculator quite yet until we get a little bit further down the road. So I divide by 82, so I end up with 14 over 82 is equal to 1/2 to the x over 30. Notice that I just isolated that exponential part, okay, or the base with the exponent on it. And now I have something that is in exponential form, but I don't know how to solve it. So let's go ahead and change it over to logarithmic form. I'm going to move up here really quick. So I'd have log base of 1/2 of 14 divided by 82, that would be that argument there, is equal to the exponent. This time our exponent isn't just x, it's x divided by 30. Okay, so then our next piece is that we're going to want to try and still get x by itself. So if I multiply both sides by 30, I have that x is equal to 30 times the log base 1/2 of 14 divided by 82. Now that seems like a lot, but we can just plug that straight into our calculators. Okay, so when you do this, a couple of things to note is in your calculator, you are going to plug in 30 times the log, and then you'd have parentheses, and you want to do the argument for it first, so it would be 14 divided by 82, comma, 1/2. Okay, and when you do that, your x value should be equal to 76.5 seconds. That's rounded. Okay, so that's kind of how we do a half-life question with these. Now let's go ahead and talk about interest. Interest tends to be a place where we use exponentials a lot, especially in the real world. Things that you might see interest rates with, loans, credit cards, savings accounts, any of those things you can either gain interest or lose or like pay interest, okay? So like a savings account, you might get money back from having your money in that savings account. Whereas if you have a credit card and you have credit card debt, you're going to be paying interest because basically credit cards are like the bank giving you a loan for a short period of time. And the goal is that you pay it back. And if you don't pay it back that month, then you have to pay interest on it. So you're paying the bank to borrow that money. Whereas for a savings account, more so the bank is actually borrowing money from you. And so they will pay you interest for having that money, okay? So there's two different kinds of interest rates. There's a simple interest rate and then a compound interest formula. Most credit cards and things like that will use a compound interest formula in some way, shape, or form. But it's important to note what a simple interest formula rate is as well. So for simple interest, we have the formula would go like this. It would say A equals P times 1 plus R to the T power. Okay, A would be your total amount. P would be your initial amount. R would be your rate. And T is the time. Now, simple interest formulas actually kind of make sense because basically this is saying you're going to take your initial amount that you have, P, and you're going to multiply it by 100% plus whatever percent the rate is. And you're going to multiply it by that T number of times, okay, to get your total amount. So an example of this would be like if I loan you $100, but I tell you that I'm going to charge you a 10% interest rate, okay, 10% interest rate. Then I could go ahead and say, okay, well, we have P is 100, and then the interest rate would be, I would multiply that by 1 plus 0.1, because the rates are in decimals, and then the time would be the amount of time that that loan takes place for, okay? Compound interest formulas, which tend to be a little bit more common in the banking world, use the same number of values. So A would be your total amount is equal to P times, and this is where it's a little bit different. We'd have 1 plus R divided by N. And then this would be to the NT. The main difference here is the N here, okay? And the N would be the number of compoundings. So if your interest is compounding yearly, that value would just be 1. And ultimately, we would be back up here at a simple interest formula, okay? But sometimes banks compound things monthly. So that means that you're basically paying interest every month to on the value of that you have, okay? Or maybe you have a bank that compounds daily. I always tell my students this story that I actually had a car loan that I was trying to pay off, and I called the bank to see how much I owed on the bank or owed to them, and it was more than they could accept over the phone, and so I had to write them a check and mail it. But the problem is that my interest rate was compounded, or my interest was compounded daily, which meant that by the time that the check arrived in the mail to the bank, it was going to be, I was owing more than what I was owing that day that I was talking to the person on the phone. So we had to like calculate out how much we thought it was going to be after those couple of days that it would take for that check to get in the mail. It was a very weird situation. So just know that there's different kinds of compounding as you're moving forward into adulthood of things to look for. Okay, so let's go ahead and use these because I want to show you kind of how these. Okay, so here's an example. Mrs. Smith invested $400 in her savings that had a yearly interest rate of 7%. Determine how much money she would have after 1 year if her interests were compounded yearly, quarterly, monthly, and daily. So 400 here would be our P value, our initial value. 7% would be our rate, which remember rates we want to write as decimals, so this would be 0.07. So if we are compounded yearly, that means that our N value would be equal to 1. So I'm just going to plug these values into our calculator, or into our equation. So I'd have A is equal to 400 times 1 plus R divided by N, 0.07 divided by 1, raised to the N1 times 1, because we have 1 year. Okay, so I should have written that X is equal to 1, or T was equal to 1. Raised to the first power, essentially. So if you were to plug that into your calculator, you would end up with A being about $428. Okay, now let's see what changes when we do this quarterly. So quarterly means 4 times a year that we'd be compounding. So you'd have N is equal to 4. Okay, so still plugging the same thing in. A is equal to 400 times 1 plus 0.07, this time divided by 4. And then we'd have that raised to the 4 times 1 power. Okay? Okay, so if we plug that into your calculator, we would have A would be equal to $428.74 this time. So notice the difference isn't that big, but there is a slight difference. This is only $400. Imagine if this was $400,000. You would make a lot more money based on how the interest was compounded, okay? How about monthly? Go ahead and try monthly and daily. Go ahead and press pause. Monthly, you would have 12 months. Daily, we're going to assume that this is not a leap year, so we're going to go with 365. Okay, so give that a try, press pause, and then come back to check your answers. Okay, so for monthly, we would have A is equal to 400 times 1 plus 0.07 divided by 12, raised to the 12 times 1 power. So this would be, in our calculators, if we plug that in, A equals 428.92. And then for daily, we'd have A is equal to 400 times 1 plus 0.07 divided by 365, raised to the 365 times 1. This would be A is equal to $429. Okay, so notice only $1 difference from yearly to daily, but if your loan or if the amount that you invested was more than $400, you would make more than that. Okay, so yeah, I guess the only last thing that I wanted to just bring up, something that was always kind of confusing to me was this part of this equation where we're dividing the interest rate divided by 4. If you hear on credit card advertisements or car loan advertisements this thing called APR, that's your annual percentage rate. So if 7% is your annual percentage rate, that means that you're paying 7% over the course of the entire year. But if we're compounding quarterly, then we would take that annual percentage rate, that total percent that you're paying in interest, and you divide it by 4 so that you're not paying the whole 7% every single quarter. You would be paying it you'd be paying 1/4 of it every quarter, okay? So that's kind of where that comes from. Okay, let's take a look at another example. A person invests $500 into an account that earns a yearly interest rate of 4%. How much would this investment be worth in 10 years if the compounding frequency was once per year? Okay, so we're going to go ahead and say A is equal to, our p-value would be 500 times 1 plus, our rate is 4%, so 0.04, divided by the number of compoundings per year, once per year. So this would be divided by 1 to the n, which is 1, times, that's n, times t. T would be 10. Okay, so if we plug this into our calculator, we would end up with A is equal to $740.12. Okay, $740.12. So you made $240 by just putting your money somewhere in an account that earned some interest rate. So, okay. Let's go ahead and extend that, okay? So if, on the other hand, the interest was compounded quarterly, why would it not make sense to multiply by 1.04 each quarter? Okay, we kind of addressed this on the last slide. So think about that for a second. So the reason that we wouldn't multiply by 1.04 on that last one, the last slide that we just saw, we had 500 times 1 plus 0.04 divided by 1 to the, it was 10th power, which really we could have rewritten this as 500 times 1.04 to the 10th power. So that's where they're getting this 1.04 from. Why doesn't it make sense if they're compounding quarterly? Well, if you're compounding quarterly, you'd be dividing that interest or that interest rate by 4 because you're not paying 4% every quarter. You're paying 4% over the course of the year. So for this, we'd write some sort of a statement that is like when compounding quarterly, you must divide the interest rate by 4, something like that. So you would have, essentially we'd be multiplying by 1 plus 0.04 divided by 4, or 1.01 if you were to calculate that out, okay? Okay, last question here. Calculate how much the investment should be worth after 10 years of quarterly compounding. So after 10 years of quarterly compounding, we would use the same equation. A is equal to 500 times 1 plus 0.04 divided by 4 raised to the, we have 10 years of quarterly compounding, so 4 times 10. Okay, if you plug that in, we would have A is equal to $744.43. Okay, so that's it for this for 7.6 with some interest stuff. There is a book assignment for this, as well as one interest question that is written on a different page in OneNote. So make sure that you're doing both of those assignments and turning both of those in. Have a wonderful day.